Um, Hello everyone, my name is Yiğit Varlı. I'm working at AWS load balancing team for the past 2.5 years. My team is responsible for the development and maintenance of the load balancer platform that is built on top of ELB, which is used by almost all the Amazon and AWS services like EventBridge, Kinesis, Amazon.com, Prime Video. Today, I'm gonna talk about the tail latency in heavy load systems, but as a disclaimer, see me as some builder from the community rather than someone from AWS because I'm speaking on behalf of my experiences. All right, let's start with the agenda for the day. So we will start with the latency and tail latency. We will discuss what are these, what are the differences, why does tail latency matters. Then this will create a good foundation to discuss why load balancing is important, and we will go over the load balancing across different layers in a nutshell. So in large-scale systems, only load balancing is never enough. So we are gonna go beyond the load balancers and see some methods that is used to scale gracefully. Then, as every food has taken its taste from sauces and spices, of course, we have some secret sauce on top of everything. So let's start with the latency and tail latency. So I think everybody would agree me that this is one of the most annoying things you have experiencing in the internet. Consider that you are doing a shopping in Amazon.com or you are watching a video, a series in Prime Video, and you do see this circle. Of course, there are lots of possible reasons, but one of them is not having a capacity and not balancing the loads properly. But we can say that if there is a kitty in the video, it makes it a little more bearable. All right. So what is latency? We define latency as transferring a data from a point to another point in the network. And there is a group called tail. This group experiences high latency, and we do call this latency as tail latency. As you can see in the graph, we have relatively similar on the average, but there is one response getting so much time. This is identified with the 19th percentile. So we call this P99. So assume that P99 is 1 second. So this means that there is 99% chance that our request will gonna take less than 1 second. And the 1% of the request gonna take more than 1 second. This doesn't necessarily mean it's gonna take 1.5. It can be 10 seconds as well. So you can say that this is 1 in 100. Why do we care this so much? So let's talk about the numbers. So there's some research made by Google and Amazon, and Google mentions that 500 millisecond increase in the latency causes websites to lose their 20% of the traffic. And this is obviously affecting their page ranking as well. Similarly, there was this data for Amazon is from 2006. I couldn't find a recent one public. So we claim that 100 millisecond increase causes 1% of the sale decrease. So we can imagine this number may be even higher because we are now talking about milliseconds in this technology age. Similar research conducted by the Cloudflare as well on the mobile applications. So you can see from the graph that once the load time of mobile application increases, the conversion rate of the application decreases. So these numbers are from the AWS Prime Day 2024. We have numbers back to 2015, I guess, maybe even past. So you can see that like DynamoDB is having high availability with single-digit millisecond responses and peaking at 146 million requests per second. We are not mentioning like per minute, per hour, like it is per second. So if you imagine like 1 in 100, like this points, like this corresponds to 1.5 million. And we can say that like in general, like small latency is amplified by the scale. So we say 1.5 million, but it is even affecting more. Similarly, Elasticache also stored more than quadrillion requests and peak over 1 trillion requests per minute. And some teams, Prime Day teams, use QuickSight and executed 1.6 million queries. So from the numbers, as you can imagine, we also mentioned there are many reasons, but one of them is having no capacity, not enough capacity, or even though you have the capacity, you are not balancing properly. So we will discuss a bit on the load balancers across different layers. So we are going to talk about 3. So one of them is hardware load balancers, and we have network load balancers, which are known as AWS NLB, and application load balancers as AWS ALB. So like the hardware load balancers are physical devices. I will deep dive into this more. And the other ones are working in the software level. So if we discuss about the hardware load balancers, these are physical devices sitting on top of the rack in the data warehouses. So obviously, like as similar to other load balancers, these are providing high throughput, low latency. As we mentioned, these are built specifically for this purpose. Their purpose is to balance the load physically. So their circuits are specifically built. We call it ASIC, application. I forgot the application-specific integrated circuit, if I'm not mistaken. So these are very expensive devices and physical devices. So these require maintenance. You cannot simply do update on the software. You need a proper team that should go to data warehouse and do regular maintenances. So which is building another cost. So they are not cloud native, obviously. They are not elastic. You cannot simply go and say, oh, like I need more capacity, like I need to scale more on the another region, and you cannot easily move that like in seconds. You need a proper planning. You need to plan it for like 1 week, maybe like even months ago. So this is obviously not really kind of creating a bottleneck for most of the companies working in very high speeds. But it might be best for like some agencies with compliance reasons, like they can build it on-prem and use hardware load balancers. And if you do care, like maybe like even single-digit millisecond latency, you might go for this. So network load balancers, these are unlike software hardware load balancers. These are software load balancers working on the transport layer, which is L4. So this has static IPs, like you can assign these LBs as targets to another LBs, like, or you can route traffic to these ones. This is important because in ALBs, application load balancers, this is not possible. And obviously, like we are talking about elastic load balancing, ALB and NLB, these are elastic, and this will scale up with your needs in seconds. This is working really well with the volatile real time because actually like you can see the cons, but this is also at some point an advantage because NLBs don't do deep inspection on the packets, like you don't read the content. This saves you a good amount of time. So we do say no HTTP routing and limited observability compared to LBs. It is because from the first reason, there is no deep packet inspection, so you don't know the content. What you know is you know the target, like you know the IP, you know the port, and basically you route traffic according to that. And limited observability because, again, the same reason. So it is best for, you want fast TCP level routing at scale, you need to preserve client IP, use static IPs. If you want to do non-HTTPS protocols and doing TLS pass-through. So I want to specifically mention like what is like TLS pass-through. So basically, in load balancers, the TLS offloads on the load balancer, which means you're decrypting data. But if you have some compliance requirements, maybe for HIPAA, you can choose to pass through this decryption state, and you can go ahead with decrypting that in the server side. So yeah, this is an advantage where you don't have an in ALB. For the ALBs, this has doing deep inspection over the contents. And you know the paths, you know the headers, you know the cookies. So you have wide variability of options to create rules. You can go and say that if this request comes to /API, just route that traffic to target group 3. Maybe you have another rule, like you had some endpoint that is not even in your application. So you can basically say that if someone do a request other than this endpoint, just return 404. You don't even really care about handling that request in your application. So it has native support for Lambda. Unlike NLB, you can put targets, Lambda targets to ALBs. And it supports blue-green deployments, which means like you can basically deploy a new code and route 10% of the traffic, and remaining 90% of traffic can route it to the previous version that you know it is working healthy. And similarly, like you can use the same way to do A/B testing. You can just route traffic, 10% traffic, like 15% traffic to another application. Cons, like it is having slightly higher latency than NLB because we are doing a processing on the contents, not suitable for non-HTTP protocols like TCP, UDP. So it is best for, in general, modern web applications because we do really care about the paths, cookies, and all of that. So this is the summary of differences, which I took from the AWS documentation. If you just search for summary of differences, ALB, VC, NLB, or AWS, NLB versus ALB, you will find this page. So some of the best practices on load balancers. Try to have multiple AZs. This is to provide high availability. People are like inclined to think that having multiple AZ load balancers will cost them more, but in general, like it is costing almost equal prices. Maybe like I don't have the real numbers, but even with like less increments. So use multiple ACs. So assume that you have an impairment in one of the AZs. What you can do? So there is a service called ARC. It is called application recovery something. I forgot to see. So you can enable zonal shift. So you can go ahead to ARC and say that I want to take my traffic from AZ1 to AZ2, and you can specify the time. Like you can basically say, I want to do it for 1 day. So you can take that impairment, AZ impairment quickly. So we have cross-zone load balancing. So assume that in one of the targets, I can show actually this example. Like you see that we have 2, 3, and 2. So if you haven't cross-zone load balancing enabled, you would have 33% of the traffic routed to each target group. So which means that for the first target group, you will have 16.7, and for the second one, you will have 11%, 11%, 11%, and for the other one, similar to the first one. But if you have cross-zone load balancing enabled, it will be distributed equally for each target, not each AZ. So this might help you to reduce your overall latency because for the first target group, for example, you were giving 33% traffic to the 2 instead of 3. So please make sure to have auto-scaling groups enabled for the targets and do it very fast on the scale up and very slow on the scale down. What I mean is for example, you do scale up on the CPU utilization, do it for 60%. But for the scale down, you wait more than scaling up. You wait for less CPU utilization to achieve and stay in that area for more time. Health checks. Health checks are really important. Sometimes we are inclined to do some simple health checks. Basically, you do ping, which is returning 200 healthy. But try to have a deep ping other than the 5 minutes. All right. Try to have health checks properly, integrating with most of the services that you have. And try to enable access logs, which might help you to debug, but in cost of a little more in the cost. So we thought that it is not enough to scale beyond load balancers, but how we can achieve. So as I mentioned, component level variability is amplified by the scale. We do have an example. So you have a 10 millisecond in general, but with P99 of 1 second. So if you're needed to get requests from 100 such servers, then there is 63% chance that that request will take more than 1 second. So this is the graph showing that, taken from the Google's paper, Tail at Scale. It's a good read. I would advise you to go and read. Why does variability exist? There are many reasons. There might be a garbage collection behind the scenes, but not in all the devices. One of the devices might be working in power saving mode. There are many things. It would be great if we didn't. So how do we live with latency variability? We can put them under 2 titles. So one of them is short-term for the request itself, and we have some long-term adaptations for coarse-grained, in the coarse-grained. So let's start with the short-term adaptations. So we can start with hedging. Hedging means basically sending multiple requests. This is most applicable to the read-heavy ones. So you might think that we are increasing this 4 times. It might cause more issues. So yeah, you are right. We can be more clever and we can wait a little bit more, maybe 10 milliseconds. Indeed, Google did this experiment. They sent more requests with the P95, and their P99.9 was 1.8 seconds, and they were able to decrease it to 74 milliseconds. It is a huge improvement. And also we can be, this was successful with just 2% increase in the load. We can be even more conservative. We can tie this request. I won't go into details, but once one of the requests, yeah, I checked. No worries. I won't go into details, but you can tie this request, monitor the replica queues, and one of them started to request, you can cancel the other one. So you don't have any more load, even that 2%. This is the results from the Google's paper. So if we were to do that for in larger scale, like we are inclined to do, like make partitions equally, but it is not always possible because there are variability. So I want to start with micro partitions. This is really similar to data sharding, but it is working inside data sharding. We don't talk about this so much, but it is everywhere in, like, mostly in the databases. Also, DynamoDB has a reInvent talk around this, advanced scaling techniques in DynamoDB from 2018. So basically, we are creating shards, but inside each shard, which I will show here, we are creating micro partitions. And then we are having some metadata associated with them. So instead of like having the multiple shards replicated, once you have the hot partitioning problem, you can go ahead and scale up the partitions instead of whole shards and do the changes on the metadata table. And the last one is latency-induced probation. Like, this is not available in ALB, but you can achieve it using AWS Global Accelerator. You can integrate with Route 53 latency-based routing. So there are many ways. But basically, what you do is that it might sound counterintuitive, but for example, like P99 of one of the servers is more than 1 second. Then we can take this out. We do reduce the capacity, but like we do increase the overall latency of the system. Then we won't put this like in unhealthy situation. We will monitor, and once it is available, we just put it back. So as I mentioned, there are some secret sauces behind the scenes. So what are these? So LB prewarming, like this is mentioned as LCU reservation. So for example, you are doing a launch in a service and you might have unexpected traffic spikes. So not every time, like, because like scaling is not really easy and taking some time. So you can mention that I'm expecting to have this many traffic, so make the load balancer ready to achieve this traffic influx. So this is one of the things, and very important. We have Direct Connect. Direct Connect helps you to create physical connection between your on-prem server with the AWS services so that you can do requests to AWS services without going to public network. This is for security, increased security, and also you don't have unnecessary network hops. Private link, like private link and VPC peering is similar to each other. Private link is like you expose an endpoint or any other service. Then you can connect this via private link to this endpoint, and you can query as if they are in your VPCs. But this is one way, not bi-directional. So, and AWS services has their VPC endpoints. So you can connect to that endpoint, and you can query DynamoDB, for example, without leaving the Amazon network, which will help you to save some network hops in between. VPC peering is very similar, but it is like peering the VPCs. Like you have, like it is behaving as you are in the same VPCs. Even like VPC peering is, in terms of latency, much better in most of the situations because you don't have the cost of ENIs in private link, but like this is bidirectional. So you wouldn't, if you don't do that if you don't want to give full access to your VPC, basically. Of course, there are some security measurements that you can take, but yeah, if you want to just expose an endpoint or API in your application, you just use private link. So if you say it was too long, I didn't even listen. So we discussed about tail latency. We called that the tail is the group that experience high latency. We discussed about hardware load balancers, network load balancers, and ELBs. Discuss about their pros and cons. We discuss about hedge requests, tied requests. These were sending multiple requests, but in clever ways. We discuss about long-term adaptations, which are micro-partitions, selective replication, and latency-induced probation. And we discuss about some other AWS technologies that we can leverage to scale further. Yep, thank you so much. I appreciate your time.
Thank you, Reed. Is there any question for him? We can take one question. Okay, I think
Thank you.
Yeah, thank you so much.